Okay, hello everybody, good afternoon. Steve Koslin wrote a really nice paper in 1999 with the title, "If Neuroimaging is the answer, what is the question?" And surprisingly, it hasn't been cited that many times, I think 150 times or so, which is for Steve Koslin from 1999 is not that much. But I want to talk about the question in the context of MVPA models. If MVPA models are the answer, what is the question? Because I think we implicitly assume that there's one correct interpretation of MVPA models, but I personally believe that's not the case. We first need to specify the question that we actually want to ask, and that then tells us or constrains us in the answers we can give about the interpretation of MVPA models. So do we have, Chris, do we have a laser pointer here?
You can use the mouse.
Oh dear, okay, yeah.
You have the screen in front of you.
Okay, good, so I'll try that. Okay, so what's the question that we want to ask with MVPA models? And for that, I think it's instructive to look at, well, the answers that people give in papers. Yeah? So here's one that I'm going to read out. Yeah? Hippocampal activity in the study was correlated with amygdala activity, supporting the view that the amygdala enhances explicit memory by modulating activity in the hippocampus. Here's another one. We tested whether pre-stimulus alpha oscillations measured with EEG influenced the encoding of items into working memory. And I think these are rather typical answers that are given in neuroimaging papers. And if you look, what's happening here is that people here use causal terminology. Yeah? The amygdala enhances explicit memory by modulating activity in the hippocampus. The EEG influences the encoding of items into working memory. Yeah, these are all causal answers. So I maintain that we often want to ask causal questions to our data. So I'm going to talk about the causal interpretation of MVPA models. Can we use these models to gain insights about the causal structure in our data? And for that, I first want to talk a little bit about what type of questions we can actually ask, what type of causal questions. Well, first of all, you can ask causal questions about processes in the brain. How does one brain area modulate another brain area? You can also ask questions how certain tasks cause brain activity. How are certain visual stimuli encoded in the brain? And the task is the cause of the effect, the brain activity. Or you can ask the question, how does the brain give rise to behavior? How does the brain cause behavior? And I believe that ultimately that is the most interesting question to ask, because we want to understand how does the brain give rise to cognition. And if there is a disorder of cognition, what has gone wrong in the brain? And what changes should we instantiate in the brain to cause an alleviation of the symptoms of some cognitive disorder? So these are all causal questions. So to better understand how MVPA models can give us insights into these questions, let us first talk a little bit about what is causality, what are fundamental causal questions. And this, again, is a very difficult and almost philosophical topic. Yeah? So first of all, what do we mean when we say X causes Y? So for instance, if I go over there and switch a light switch and the light here goes out, then I guess all of you would agree that the light switch causes the light going off. Yeah? But what if there's some faulty wiring in the light switch? And I switch the light switch, but only 90% of the cases the light changes, goes on or off. Yeah? Would you then still call the light switch a cause of the light going on and off? Probably you would. But what if the wiring is so faulty that whenever I switch the light only changes in 50% of the cases? So it's essentially random. Would you still say that X causes Y in this case? So the answers to these questions depend very much on what concept of causality you're working with. Should it be deterministic, probabilistic, and so on? So again, I think you first need to specify what does X cause Y mean, and then you can give answers to whether a brain region is a cause of some behavior or not. And for different frameworks of causality, with different definitions of causality, you might get different answers. Second, what is a causal variable? Of course, the light switch, that is rather simple. Turning the light switch can be a cause of the light going on and off. But for instance, what about gender? Men tend to be taller than women. So is it a well-formed statement to say gender is a cause of body height? is it conceivable that I take some subjects and assign a treatment in a control group where for some subjects I assign the gender male and for other subjects I assign the gender female, and then I study the effect on body height? No, of course not. I can't randomly assign gender to subjects. So is gender a meaningful causal variable? In some frameworks it is, in other frameworks it is not. In our context, what about fMRI recordings? Is fMRI data a meaningful causal variable? So if you say with some framework fMRI activity in area A causes fMRI activity in area B, what do you mean by that? So usually when you make a causal statement, you're making predictions on the effects of interventions. When you say fMRI region A causes fMRI region B, what is the intervention that you're specifying? Are you claiming that if you pump oxygen into brain area A, then something will happen in your fMRI signal in brain area B? Or something completely ridiculous, are you claiming that you open up MATLAB and change your variable in fMRI area A, and then you hope to see a change in MATLAB in fMRI area B, the representing variable? Well, obviously not. But what is the level, what's the intervention that you're predicting? Without making that intervention explicit, you're not really making a well-formed statement. Third, under which assumptions, if any, can we infer causal relations from non-experimental data? If the light switch, if I just see the light switch turning by itself and I see the light going on and off, can I infer just from looking at that whether the light causes the light switch to move or whether the light switch causes the light to go on and off? And if I want to make those inferences, do I need any assumptions? So in general, in machine learning, if you treat it from a machine learning perspective, there are two words, the word of doing and the word of seeing. And we need some assumptions, mathematical assumptions, to move between these two words and relate these two words. And in some frameworks, these assumptions are made more explicit. In other frameworks, they are not really made explicit. So this is what I'm going to talk about a little bit. So let's talk more precisely about the framework of causality I'm going to use today. And that's the framework of causal Bayesian networks developed by Judea Pearl and Peter Spertis and his collaborators. And they both wrote a book about it that was published in 2000, or two books. And it's essentially the same framework that they describe, which is really useful because you can look up all the theorems and all the theory written up in two different ways, which really helps because it's very dense if you read these books. So what's the framework of causality that they use? They say that xi, and that is some random variable. You can think of it as maybe neural activity in brain region I, is a cause of xj, some other neural activity in brain region xj, if there exist values of xi and xj such that this here holds. And this here says, you look at the probability distribution of xj, so how likely are different outcomes of xj, for instance, firing rates. Given that you intervene, that's the do operator, you change the activity in xi and set it to a certain level. Maybe you set it to a firing rate of 100 spikes per whatever. And you need to find one setting to which to set xi such that the probability of xj is different from the one that you would have obtained without intervening. So as long as you manage to find some setting, some intervention that changes the probability distribution of certain events occurring, then you say that xi is a cause of xj. So it's a probabilistic concept of causality. And I really like it because it's a very general framework. For instance, if you take an aspirin, then sometimes your headache becomes better, sometimes it goes away, sometimes it doesn't change. But that's okay, because you can do some change to the probability of having a headache by taking aspirin. So you say aspirin is a cause of headache relief. It doesn't need to be deterministic. So in this framework, how do we move between this world of doing, these interventions, and the world of seeing, of passive observation? And for that, we need to talk a little bit about how causal relations are expressed in this framework. And in principle, there are three building blocks of causal networks here, or directed acyclic graphs: the chain, the fork, and the collider. And with these three directed acyclic graphs, you can build up any more complex network. And these causal structures, that live out there in the world somewhere, but that are not directly observable to us, they generate some data. And we need to have some assumptions to relate the data that we see to the causal structures that have generated them. Yeah? We need to have mathematical assumptions that allow us to move between these two worlds. And the two assumptions that we need are the causal Markov condition and faithfulness. So the causal Markov condition essentially says that all independence relations that you find in your data, all independence other way around. All independence relations implied by a certain directed acyclic graph, you also find in your data. And faithfulness says it the other way around. In your data, you find no additional independence relations beyond those implied by its DAG. I tell you in a bit more detail in a few minutes what that means intuitively. But now let's go to this chain here, and let's ask what independence and dependence relations such a chain generates in your data. You will find that if your data is generated by a chain, that x1 and x3 are dependent. So dependence, the more general case of correlation, can also be nonlinear dependence. Because x1 is a cause of x3 via this via x2. If, however, you condition on x2, if you know what happens at x2, then this dependence vanishes. So in the linear case, they become uncorrelated because x2 blocks this path from x1 to x3. The fork has the same set of dependencies. x1 and x3 are dependent marginally because they have this joint common cause x2 that induces this dependence. But if you remove this joint common cause by conditioning on x2, then x1 and x3 become independent. The collider is a bit different. The collider generates data where x1 and x3 are first independent because there's no causal relation between them, but they both cause x2. So if you condition on x2, you render x1 and x3 dependent. And because they now share information, they provide a joint information to x2. So if you're willing to make these two assumptions, causal Markov condition faithfulness, which you can't test, you just have to make and buy these assumptions, then you can now relate the dependencies that you find in your data to the structures that can have generated your data. So if you find this set of dependencies, then you know the fork and the chain cannot have generated your data. They are not consistent with your data. Only the collider is, or more complex structures with hidden variables. So this is the way in which in this framework you move between the world of doing and the world of seeing. You look at the dependencies in your data, and these dependencies tell you which causal structures are consistent with your data. And sometimes you're really lucky and only one causal structure is consistent with your data, then you're done. And sometimes you can only rule out some causal structures but not others, but maybe you have learned something then as well. So about the intuition behind these assumptions here, the causal Markov condition is a bit debatable because for Judea-Pearl it's a theorem and for Peter Spertus it's an assumption. So that depends on whether you think that structural equation models are the right way to model the world or not. Faithfulness is a bit easier to understand. Faithfulness essentially says that nature doesn't fool you. That if there is a causal relation, a causal influence from one variable to another one, then you see a dependence in the real world. But it's also conceivable that if you have two causal variables, that they cause each other via multiple paths, and these paths exactly cancel each other out. Yeah? And faithfulness essentially says this exact parameter tuning such that causal paths exactly cancel each other out and you don't see a dependence even though there is a structural relation that is ruled out. Unfortunately, though, it's not testable. Okay, so now you know the framework a little bit that I'm working with. And now how does this all relate to encoding and decoding, to normal encoding models and MVPA models, and how can we learn something about the causal structure with these models? Well, for that, let's briefly talk about what sort of hypotheses encoding and MVPA or decoding models test. So in encoding models, you're looking at some test statistic, some property of your data, given your experimental conditions. And you're asking the question, does a brain state feature, some fMRI voxels, some spike rate, whatever, change across experimental conditions? Maybe the mean, you want to test the mean, maybe you want to test the variance, any property of your data that you choose. So essentially, your null hypothesis is my class condition, my class labels, are independent of my feature. And if I have sufficient evidence to reject that, then I say, okay, fine, xi is a relevant feature, and you might paint a blob in your fMRI result in your paper. Decoding models do it the other way around. So they use all your features to predict the class label. So they ask the question, does the brain state feature help in decoding the experimental condition given all the other features? Or could I also achieve this decoding without that one feature? And how do you test that on reader data? Well, you can either plot these weight maps, or something that people also often like to do is that you first train a decoder with all your features. Then you take one feature, you permute that one feature, and then you retrain your decoder. And in this way, you've made sure that this one feature that you permuted cannot provide any information about your class labels anymore. And if then your performance drops relative to training with all features intact, then you know your decoder needed that feature to perform well, and it's a relevant feature. And what you are trying to test with that is a marginal independence test. You're asking the question, given all my brain state features except the ith one, does this ith feature still provide information about my class label? And if it does, then you say, okay, this is a relevant feature, and it might get a blob in your paper in the end. So how does this now relate to causality? The feature relevance in your encoding models or your decoding models translates to marginal independence tests between your class labels and your features, in the case of the encoding model, or to a conditional independence test in terms of in case of the decoding models. So with encoding, decoding models, you learn something about the dependencies or independencies in your data. And that gives you insights into the causal structures that could have generated your data. Or other way around, it can rule out certain causal structures as being inconsistent with your data. So we're almost in a position now to create a table and create some set of interpretation rules. What causal structures are consistent with your data when you find certain results with your encoding or decoding models. But to make this table, there's one more distinction that we need to make. And that is about task-based and behavior-based experimental setups. So in a task-based setup, you are randomizing your stimuli. And you're studying how these stimuli cause brain state activity. In a behavior-based setting, it's the other way around. You're asking how do brain states generate behavior. And that means that a priori, we know something about the causal relations here. We know that tasks that are randomized can only be causes of brain activity, not the other way around. And we think that brain activity causes behavior and not the other way around. But except, of course, if we introduce some feedback loops ourselves. So that means that if we're using a standard encoding model, like a correlation, a t-test, SPM, generalized linear model, and we're looking at a task-based setup, then we're studying some property, so some probability of the effect, the brain state as a function of its cause, the task. So that means we have a model here that works in a causal direction. If, however, we are in a behavior-based setting, then we're trying to model how the behavior, how the brain state, so the cause, we're trying to model the brain state, the cause, as a function of its effect, the behavior. That means this is an anti-causal model that goes into the other direction. In a decoding model, this is now exactly switched. In a task-based setting, we're trying to predict the task, so the cause as a function of its effect. So that's an anti-causal model. And if we're trying to predict behaviors from brain states, then we have a causal model because we're modeling the effect, the behavior as a function of its cause, the brain state. So depending on whether you're looking at a task-based setting or behavior-based setting, and whether you're using an encoding model or an MVPA decoding model, sometimes your model are causal, sometimes they are anti-causal. And if you want to attach causal interpretations to your models, then it should be evident that you need to distinguish these cases from one another. Okay, so we are now in a position to make such a table. We say, okay, let's assume our experimental analysis is done. And if we find a feature to be relevant in either an encoding or decoding model, in a task-based setting or behavior-based setting, what is the causal interpretation of that, if any? So let's start with the easiest case. Encoding model, task-based setting, you find a feature not to be relevant. That means that your task and your feature are independent of one another, and then you know that your feature is not an effect of your task. It's reasonably simple. However, in a decoding setting, if you use a decoding MVPA model in a task-based setting, and you find that your feature is not relevant, meaning that it is independent of your task, given all the other features, does that also mean that your feature is not an effect of your task? And unfortunately, it doesn't. Because you could have the case where you have such a chain here, where your task causes some modulation in feature xj, and that causes modulation in feature xi. And then xi is an effect of your task via xj. But because xj is early on this chain, you don't need xi for decoding anymore. Any information about t is already contained in xj. And that means that xi is an effect of your task, but doesn't show up in your model. So negative results in decoding models in a task-based setting can't be interpreted. Now, even if you would be willing to interpret negative results, which is difficult in its own right. Negative results in MVPA models are difficult. So what about task-based setting? In an encoding model, when you find a feature to be relevant, then you know that the feature is an effect of your task because you've randomized your task and nothing can really go wrong here. Nice positive result. What happens when you find a feature to be relevant in your decoding model? Then, unfortunately, you have two interpretations again. It could be that your feature was indeed an effect of your task, or it could be that you have such a collider here, where you have some feature in your data, xj, that is influenced by the task, but xi is not influenced by the task, but influences this other feature. And then xi helps in decoding because you can use it to regress out noise. This is the example that Bertrand gave earlier. So if you find a feature to be relevant in a decoding model in a task-based setting, you don't know whether it's an effect of your task or whether it's some noise variable that helped because you could regress out noise. And the behavior-based setting essentially is the same case, so I won't go through this in detail. So in the end, you have this interpretation table where you have two negative interpretations and one positive interpretation, but the rest is inconclusive. In particular, the decoding models don't really fare very well. So if causal relations in your data is the answer that you want to give, or the question that you want to ask, then it looks like from this table that MVPA models are pretty useless, and that you should stick to standard encoding models. Now, when I read the literature and this discussion going on what's better, encoding or decoding models, I'm sometimes a little bit surprised because I think, why do we have to constrain ourselves to one model? There's no particular reason why we should only look at our data with one type of model. Why not train an encoding and a decoding model? Because, as I'm going to show you next now, if you do that, if you look at your encoding, at your data from an encoding and decoding perspective, and you find asymmetries, if one model tells you a feature is relevant, but the other model tells you it's not relevant, then you can learn something about the causal structure in your data that could not have been learned from each model on its own. So I think this whole fight, are decoding or the encoding models better, is a bit misguided. Use both of them and use the information that provides to learn more about your data. And I want to pick out two examples. Let's start here with a task-based setting where you find in an encoding model that a feature is relevant, but your decoding model tells you the feature is irrelevant. How can this happen? And the explanation is relatively simple. The task modulates some of your features, but not directly your ith feature. This ith feature is modulated in a chain where some other features that are being modulated by the task modulate that feature. Then in an encoding model, you find this feature to light up because there's this path from the task to the feature. But if you have all the other features in your decoding model, that path is blocked, and hence it doesn't show up in a decoding model. Yeah? So if you have this asymmetry, you know that your feature xi is an indirect effect of the task relative to the other features that you have. And you've learned more about your data. Let's look at the other constellation. If in an encoding model, you find a feature not to be relevant, but in a decoding model, it is relevant. Then you have a situation where you know that there's no path from your task to your feature, because otherwise it would light up in an encoding model. But it still helps in decoding, so it must be some noise variable that you can use to regress out noise from other features. So in a way, it's some context noise variable. And again, you've learned a bit more about the role of your features in your task. And in this way, you can fill up this whole table again, and it looks a lot better. You can't learn everything about your data, of course not. But by using encoding and decoding models together, you can learn more about your data than if you just look at these models on their own. So how can you actually use this? And is this actually being used on real data? And it is now being used on real data. I'm very happy about that. So I want to show you a recent study from the lab of Ray Dolan at UCL. And the first author is Dominic Bach, who's now in Zurich. And they investigated the neurodynamics of probabilistic reward prediction. So they had a task where they showed subjects stimuli. These were the 9 stimuli that they showed them. And every type of stimulus was related with a certain reward. And the subjects first had to learn this association. So whether a circle was filled, half-filled, or empty indicated the mean reward the subjects received for one of these stimuli, 1, 2, or 3. And the color coded the reward variability, so the variance of the distribution from which the reward was chosen. Yeah, so blue is this standard deviation, green this one, and purple this one here. And subjects had first to learn this association, and then they did an MEG study where they had some delay period, where they then looked at how the representation of the expected reward evolved over time. And they did exactly what we proposed. They trained an encoding and a decoding model, and depending on the asymmetries that they found in the activations, they plotted features as either being direct effects of the stimulus, indirect effects of the stimulus, or context or noise variables. And they then plotted this here in source space and also here over time, and nicely found that early visual areas are direct effects, later areas are indirect effects, and some areas were labeled as noise variables. So I only showed you this to show that you can indeed use this framework rather easily with standard methods that are implemented everywhere to learn a bit more about your data than you could if you think that only one of these approaches should be used on data. Okay, so let me wrap up. So to summarize, what does X cause Y mean? Very much depends on your setting. No? And I think you have to specify that. Second, what is a causal variable? Again, depends on your framework. But please, if you use causality, and if you make such claims about causal relations, either explicitly by saying A causes B or implicitly by saying A modulates B or enhances B or whatever, please try to be specific about what type of intervention you mean. That is not an empty claim that you're making. And third, when you ever encounter some causal claim, please ask yourself, is it clear to me what the assumptions are that go into this? Have the authors clearly specified what assumptions I need to make to move between the world of doing and the world of seeing? And with that, I want to briefly discuss some other frameworks about causality and causal relations in neuroimaging and ask whether they fulfill these requirements of really being causal frameworks. So Granger causality is used rather often. And I think Granger causality is a great framework in many ways, but I don't really think it's a causal framework. So you've probably seen this definition that you often have in neuroimaging journals of Granger causality. that says one stochastic process is causal to a second if the autoregressive predictability of the second process at a given time point is improved by including measurements from the immediate past of the first. Essentially, it says A causes B if the time series A helps in predicting B. And I think there are two problems with this. The first one is there are no assumptions involved here on how to move between the word of seeing and the word of doing. Granger causality essentially defines causality as an observational property, prediction accuracy. And prediction accuracy is an observational property. It's not an interventional property. And it's an interesting framework. You can certainly learn something about relations, about data, but it's not the case that Granger causality tells you or predicts the effects of interventions because it's not designed to do so. And hence, in this strict sense, it's not a causal framework. Second, my second problem with this here is that Granger never said that. You read this all the time, this is the definition of Granger causality. Let me emphasize this. Granger did not define causality like this. It's just wrong. And if you write this in your paper about Granger causality, then everybody knows that you never read Granger's original paper. This is Granger's definition. It's a bit more complicated, but it's worth looking at it. So Granger says, if the prediction error, sigma squared, of a time series y, given the past of the whole universe, is smaller than the prediction error of y, given the whole universe minus time series x, we say that x is causing y. And you can question whether a definition is meaningful if you include the whole universe in it. But essentially what the difference is, the whole universe includes every potential latent confounder. And then Granger says in his paper, and of course we can't observe the whole universe, and of course we don't have the perfect models to compute the perfect prediction error, so we have to limit ourselves. We have to say, okay, we only look at some subset of the universe, we have to make some modeling assumptions, and now I give you an example of autoregressive models and how that would look like on a small set of variables. And that's then what he ends up with here. And the difference is, in this framework here, latent confounders are ignored. In this framework here, it's not. So if you apply Granger causality, you always have to assume causal sufficiency, meaning there's nothing in the world that could have confounded your data. If you need to make this assumption, fair enough, but please be explicit about it. Finally, dynamic causal modeling. I think DCM is a really helpful and useful framework. For instance, Klaas Enno Stefan uses it to extract features from his data and shows that he can classify like responders into non-responders, distinguish them from another, to a treatment from neuroimaging data with the DCM parameters. It's really great. But causality in DCM is very vaguely defined. So Carl Friston writes, causality is used in a control theory sense, means that under the model activity in one brain area causes dynamics in another, and that these dynamics cause the observations. You condense this. This says A causes B when A causes B. This is not a mathematical definition. And when you look at how DCM, what they do is they do model fitting. How well does a model explain certain data? And for sure, you can learn something interesting about your data, and these parameters might have a meaning. They can be useful as features. But there are no assumptions or no conditions in this framework that tell you how to move between the word of doing and the word of seeing. So I personally think DCM is a great framework, but it's not a causal framework. Okay, so the papers that I've mentioned that we wrote ourselves are on my webpage, along with a lot of other things. Thank you very much for your attention, and I hope there are some questions. Hi, Jessica.
Hey, I had a question about your table when you use both encoding and decoding models. And on one specific line, you say, if that feature was not relevant in the encoding, but it was in the decoding, then it's a collider, and it was basically just noise in that feature.
Yes.
Could it just be that you lack some power because of multiple comparisons and things like that?
Yes.
Which is often like what we do when we use MVPA instead of
Yes.
encoding models?
Yes, thank you for that question. I assumed throughout my talk that we make no errors in our statistical inferences. Yeah. And you all know that this is unreasonable. So I think we need to be aware that, of course, our statistical tests have a certain power and a certain false discovery rate, and we may make mistakes. In particular, in causal frameworks, this is difficult because you are interpreting negative results. Negative results, interpreting them is not the same. It's not on the same rigorous. It's not as rigorous as rejecting negative results. Yeah. Thanks for pointing that out.
Another question for Moritz? You haven't posed many questions.
Ah. So I'll be around until Wednesday. If you want to have a discussion about causality, please do catch me anytime. Okay.
Yep. Thank you, Moritz.